Okay, Assalamualaikum and very good morning to all of you. Okay, so start from this week, we start our first lecture, which is chapter 1, Introduction to Vibrations. Okay, for the outline for this topic, which is the outcomes expected from this chapter, which is student can understand the basic concept of vibrations, identify the different type of motions, different type of vibration and degree of freedoms. So basically this is the way to understand the vibration system. Okay, so you have to know what is the elements for the vibrations, what kind of motion, and the type of vibration. So detail we go subtopic by subtopic after this. Okay, so basically in this subject we relate with the motion and also the forces, the applied force. Okay, so if there is no force, no motion, then who cares? There's nothing interested about the system, right? Because there's nothing happen, there's no motions and no deflection. Okay, so this one we're looking for that. If the system you only apply the force, but there is no motions, so which is there is no motion about the mass or anything about the system lah. So this one we call as a static. Okay, so static, which is we apply the static loading. So some kind of what you have learned in static subject, so which is you apply the force and what happened to the structure. So is it a bending, we study about the deflection, something like that lah. How strong it is, the stress strain applied. Okay, and then if we go for the motions without force, that one we call as a kinematics. It just totally is the motion itself lah. And then what we study in this subject we call as a dynamics lah. So dynamics, which is when the force and motion. So which is when you apply the force, then there is a motion. Motion means that it can be any kind of motion lah. So either can be step or can be fluctuations. But for this subject, we are more looking for the type of motion we call as oscillations lah. Oscillation, which is there is a fluctuation moving up and down, left to right, and etc. Or it can be rotational directions. So we detail out after this. So between force and motions, there is a relationship lah. Okay, so which is when you apply the force and there is a resulting motion lah. Okay, so motions can be displacement, or it can be velocity, and it can be accelerations. Okay, so it can be linear or non-linear. But for the subject, we look for the linear system lah. Okay, so which is the dynamic system, when you apply the force and there is a linear relationship with the motion lah. So normally for the for example, for the displacement, okay, so displacement is some kind of when you apply the force and then you measure the motion displacement and the coefficient that relates between force and motion or force and displacement we call as a stiffness of the system. Okay, and then for the velocity there is the damping coefficient. Okay, C, and then for the velocity they call as inertia. So inertia, which is dominated by the mass for the system. Okay, and then the motions can be a bit vary or the harmonics. So harmonics move up and down, lah. So harmonics, this is what we study in mechanical vibration lah. And apart from that, there is also the same kind of motion for the acoustic signals lah. Okay. So acoustic, which is the sound pressure. So because when you talk, there is the sound intensity. You have a move in the harmonics motion. So there is a fluctuations depend on the frequency that produced by acoustic. But we're not interested about acoustic for the subject. We are looking for the vibration. But actually, if we go in detail, there is a relationship between vibration and acoustic lah, because acoustic can induce the vibrations due to the harmonics excitations lah. But we not go in detail about that. Okay, now we go for the basic concept of vibrations. Is inherent. The study of vibration is oscillations mentioned, which is what we call vibration when there is a system, there is a vibration. So mean that there is a oscillation, is move up and down, left to right, or it can be the twisting, or it can be in the rotational motions. All of that we call as a vibration, something that vibrate. And if you go detail, electric circuits can be oscillatory voltage. So which is can see that the AC voltage, if you capture by any oscilloscope, you can get the oscillation lah. Okay, so it's depend on the frequency, normally for 50 or 60 hertz lah. But this one we didn't call as a vibration system lah. Okay, and then the air pressure, as mentioned before, this one is acoustic. Okay, so this one is not totally vibration, but it can induce the vibration if you hit the system. No? Okay, we call as acoustic induced vibrations. And vibration is usually used to describe the motion of mechanical object. So which is you have the object, which is the object have the mass, and that object can oscillate lah, or have a potential to oscillate. So which is if you give the initial disturbance to that mass, then that mass will oscillate, or you apply the force and there should be oscillations. So this one we call as a vibration system. Okay, to have the vibration system, you must have mass, and then must have the spring elements, the damping elements. If you have all at least mass and spring system, then it can declare as a vibration system lah. Because by those two parameter or those three, you can create the motions if you apply the force or give the initial disturbance to that system. So basically, vibration is you can define as a repetition of any motion after the period of time. So which is if you have this mass, for example, it can have motion move up and down, and it have their own frequency. So which is depend on the period lah. And actually the repetition is depend on the properties of the system itself. Okay, so it depends on the value for the mass and for the stiffness and for the damping coefficient for the system lah. So meaning that is related to its own natural frequency. So natural frequency is depend on the stiffness and mass. For the single digger freedom, we can define as the square root of stiffness over mass lah. Okay, so which is that's the natural frequency. So mean that if you give the any initial disturbance to the system, for example this one mass spring, okay, you press and then you release, and then this mass we oscillate, so there is a repetition of motion. So this one is vibration. How fast is the oscillation is depend on the the properties of the stiffness and also the mass. So which is that define the period of time. The higher stiffness, the times taken to complete one oscillation. Complete one oscillation means that this mass move upward, downward, and back to the initial position. So that's one complete oscillation. So that's the times taken to move to complete this motion. Okay, so that's we call as the period of time. So the higher stiffness, the shorter period of time. So the higher frequency. So vibration system I mentioned, we can should have a concept of those three elements. Mass, so which is can produce an inertia. Okay, so if there is mass and there is accelerations for the system, and then you can induce the initial force. So F equal to ma, so the relationship. Okay, so we just consider the linear system. So F equal to ma lah. So the higher mass can produce the higher initial. That's the 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 logic lah. So then we go for the spring elements. Okay, so spring element which is control the stiffness. Okay, so or we call as electricity. So for this case, the force reaction from the spring is depend on the stiffness and the deflection or displacement for that mass lah. So it's depend on the Hooke law. Okay, F equal to kx. Okay. So that's the relationship between force and the displacement. Okay, so it's depend on the displacement for the system lah. And then there is a damper lah. So damper we induce the damping force. Okay, so damping force is a relative to velocity. Okay, so which is the higher velocity can produce the higher damping force lah. So the relationship F equal to C X dot lah. So S dot or C is damping coefficient times by the velocity lah. Okay, so that's the relationship. Okay, so for the system under dynamics equilibrium, so which is there is no external force applied, and then depend on all those three elements, the forces that produced by all those three elements should equivalent to zero lah if there is no force applied lah. So which is meaning that the total initial force plus by the stiffness force plus by damping force, if you summation all of that forces, it will equivalence to zero. So that's what meaning that the system in the equilibrium. And for now, we can consider that all the motion system is equilibrium. Okay. And then yeah, this one basically the concept involve the transfer of potential energy to kinetic energy. So which is the stiffness can create the motion. So motion from that kinetic and vice versa. So detail mathematically we go detail after this. So actually for the first chapter just introduction, we not look at for the much about the equations. The detail we go after this. Okay, this one they should go for the full screen. Okay, sorry, before I forgot, please write your name and matrix number just for my attendance record. Okay, then for the motions in this subject, we are looking for the motion for the fluctuation, or we call as an oscillation. Okay, and then this kind of motion we can represent as the sine function. So the core knowledge that you should have in this subject, which is you have to know how to interpret the sine function, the relationship with the vibration. Okay, So this is the most important thing. So make sure you understand how to interpret the sine function and then make the relationship, how the motion or how the force can be uh, simplified into the sine function. Okay. So basically, if you are a mechanical engineer, you will deal with a lot of the rotating machinery. Okay, so which is any rotating components, we induce the force with this kind of motion. Okay, so for this case, we consider that the force we model as a single degree of freedom. So single degree of freedom meaning that the mass is restricted to move in the one direction lah, for this case vertical. So that's why we want to express the amount of force applied in the vertical directions lah. So the force applied in this one, so that's why we can uh, represent as a the sine, this one is sine function because we want to know in the vertical. Okay, so for example at this point, okay, so this is the amount of force reaction in this direction, so which is the magnitude is F, but now we want to uh, find the resulting force in vertical direction. So if the angle here is a theta, okay, so the force in the vertical direction is equivalent to F sine theta lah. So if we move for this, for example this one, okay, so this one depend on the theta. Theta should start from 0 in this horizontal line, and then this is theta lah. Okay, so that's why the amount of force in the force is constant, but it's due to the rotational motion. And if we want to measure the force in the vertical directions, and then to find the resulting force in the vertical direction, so this is the magnitude of the force at this instant. Okay, that is keep rotating. Okay, for this case, for example, this one. Okay, so the direction is in the horizontal. So we want to measure in the vertical, right? So the resulting force is equivalent to 0 lah. So there is no force applied because the totally is applied in the horizontal. The resulting force in the vertical should be equivalent to 0 lah. So if we move, so that's the way we can represent the force. The force is fluctuation, it's not constant force because we'll deal with the rotating machine, rotating force lah. Okay, so which is the vertical direction we can represent as a F sine omega t lah. Okay, then this is a motion. So you can see that the spring mass system, the motion is in the vertical direction, which is it move up and down. Okay, but how we want to find the displacement for this mass, because it's not constant, right? It moves up and down. So but this one also can be represented as a sinusoidal function lah. Okay, okay, you can see that this motion so this is initial position, and then when there is a motion, move upward, and then after that, okay, it move to downward direction. Okay, and then downward, and then move back to this point. Okay, so this one we call as a one complete oscillation. Okay, so one complete oscillation. So which is the mass move in upward directions and goes to downward, reach at the equilibrium position, and keep moving to the downward directions until it move upward and stay at the same position. So this one is a we call as one complete oscillation. Okay, so the times taken to complete one oscillation we call as a period of oscillation. And then uh, it's related with the omega t. So omega is frequency and t is a time lah. Okay, so omega is a which is the unit in the radian over seconds, radian over seconds. So mean that you know that for the to complete one oscillation is equivalent to the 360 degrees. Okay, so which is start from here. So it's rotate until one complete oscillation. So which is complete to one complete cycle, and then is equivalent to 360 degree or 2 pi radians. So that's the which is the angle cover in the period of oscillation. And then how fast it is depend on for example it take 1 seconds to complete one complete oscillation. So it's a 2 pi over t lah, so 2 pi radian over seconds lah. So that's relate with the sine function. Okay. uh, okay, so when we talk about the motion of object, so it just move up and down. Okay, so what you have to know that if we plot the motions, okay, uh, okay, so this is a graph, the amplitude. So amplitude here I using the x, so x which is the displacement, so unit is meter, and then versus time, because this kind of motion have a fluctuation, it's not static motion. So when the time increase there is a difference for the displacement. So t which is in the unit of seconds. Okay, so when talk about the spring mass system, there is a mass spring. Okay, so there is a motion for x. Okay, so if this mass move in the vertical direction, we consider as a motion. And how we want to present the motion of the mass as a sinusoidal. Okay, so we know that when the time increase, the displacement of the mass also increase until it reach the highest position lah. So maximum amplitude. Okay, and then it goes downward until it reach the lowest point lah. Okay, and then it's back to the initial position, and it keep repeating until you stop it lah, or you force it to stop. Okay, so the times taken from this point to store the line. Okay, so this is a t. T is a period of oscillations. Okay, so if we look at this response is actually represent the sine function. Okay, the sinusoidal function. Okay, so this is t equal to 0. Okay, so now how we want to represent into the sinusoidal. So basically for the sinusoidal, we can the sine function we can represent as a sine omega t plus the phase angle lah, for example the sine. Okay, so now we want to relate with the response that in measure lah. Okay, so a actually is refer to the maximum amplitude. Okay, so we can represent this graph. So this is a. Okay, so which is represent the amplitude of oscillation lah. And then there is a omega. So omega actually is defined as the frequency of oscillation. Okay, how fast. So which is the higher frequency, so mean that the period oscillation is shorter lah. Okay, shorter period oscillation, so mean that there is higher frequency. So that's the relationship which is depend on the period of oscillation. Okay, so the frequency there is a two unit for the frequency if you measure in the linear frequency or angular frequency lah. Okay, so f equal to 1 over t lah. Okay, so this is the frequency. So which is t is a time taken for the one complete oscillation lah. Okay, so one complete oscillation actually is cover for the 360 degree or 2 pi radians lah. So that's why so this one unit is hertz. And then if you want to convert to omega is equal to 2 pi f. Okay, so because we want to read with the radian over seconds. So one complete oscillation is equivalent to pi and then times by the frequency. Okay, so here the units are equivalent to radians over second. Okay, so that's the relationship how fast it moves. And there is also actually the phase angle. So the phase angle actually is depend on where it start lah. Okay, so for example, if your graph doesn't start at zero lah, so sometime when you do the measurement you got this kind of response lah. So when t equal to 0, there is a x naught lah. Okay, so this is the angle lah. So if you represent into the polar plot, okay, if you draw a circle, okay, and then where it start, the angle here is represent the phase angle lah, theta. Okay, so this is where the theta is coming from. Okay, so this is how we represent the motion into sinusoidal function lah. Okay, so basically this is the mathematical equation and we can relate the motion lah. So you know that this is when start from here, the theta equal to 0. Oh, sorry, the phase angle, the psi is equal to 0. So that's why we can just represent as a sine omega t lah. So this one if start from the 0 phase angle. And then when the time increase, there's motion lah. So meaning that the angle also increase. So it's depend on the sine angle lah. So what is the angle is depend on the frequency of oscillation and the times lah. So for the 1 seconds, so you can just times by uh, 2 pi over t lah, 2 pi over 1. For the 0.1 second, what is the angle? Okay, so because the angle is the difference for every times lah. So if you want to capture for the at 0.1 seconds, what is the position lah, and then you have to find the angle. So sine, what is the value for the angle lah? So get angle is omega times by t. So 2 pi radian over second time by second, so you got radians lah. So all the unit is in the radians. Okay, so this one actually is the most important part in this subject. So you have to know that the relationship for the sinusoid, because after this, every chapter, every subtopic, all of the motion, you will find sine or cos lah, sine function, cos function. Actually, sine and cos is just the same, but just the different phase angle lah. So this one is a sine lah. So sine. For the cos, if you plot, so it start from this point lah. Okay, so this one is cos lah. Cos actually is equivalence to the sine omega t plus pi over 4. So pi over 4. Okay, so 90 degree. Pi over 2, sorry. Pi over 2. 4 is 45. Okay, so that's the relationship lah. So after this, you will find sine, cos, but that's why it's very important for you to understand, to relate with the motion, sine and cos with the vibration system. Okay, so back again. So I think should go for the full screen. So you can see that the motion, okay, so the motion is up and down, up and down. Okay, so that's happened. Okay, so if you have the machine, so when the machine is running, actually there is motion move up and down, or it can be left and right. So it's depend lah. So if you want to study motion for the vertical, then you can study about the vertical motion lah. So this one is simple single degree of freedom. So okay, so if you interested for the more degree of freedom, which is will be detailed after this, you have to measure for every nodes lah. Okay, so actually this one is very important lah, especially if you go for the industrial application. So you want to measure the level of vibrations lah. So if you put a machinery, then you do the measurements to measure the vibration response, and this is what we get. Okay, actually it's a lot of combination. So because the industry, there is not simply a single degree of freedom, there is many degree of freedom, but actually you can split by the frequency lah. So if you know that this is frequency of the vertical motion, and then you know that this is the frequency for that vertical motion, and then you can know that what is the intensity of vibration. Okay, so you can measure. So normally for the industry, we measure the vibration in the unit of velocity lah. Okay, so to know that the vibration intensity, so if there is high vibrations, so meaning that you have to solve lah that high vibration issue. Okay, so meaning that you have to back again to the system. So as mentioned, the normally is due to the resonance or due to the faulty machinery. So you have to identify lah. If the you found that the frequency of oscillation for the vertical motion is close to natural frequency, so mean that there is highly possibility the high vibration is due to the resonant issue lah. So mean that you have to tackle how to solve the resonance. Solve resonance, either you change the operating speed to ensure that the operating speed is not coincide with the one of its natural frequency, or you can change its natural frequency lah. To change natural frequency, because as mentioned before, the natural frequency is dominated by its mass and also the stiffness of the system. So you can change the mass, or you can change the stiffness lah. So you can change the stiffness to stiffen the structure. You can keep it higher natural frequency. Okay, or you can use there is a study called as a mass tune damper. Okay, so which is you put the mass to the system, additional mass, so to control to control its natural frequency. Okay, so basically this is a relationship lah. So I think this one the last slide for today. So difference between control system and the vibration system. Okay, so for this one is control system. So control system, which is there is input, and then the system, the output, and then there is the sensor, which is to feedback the system. So meaning that to control the system. Okay, so mean that if you want to for example, for the vibration system, for example, you can still control. For example, you can use the damping system. Okay, so for example, the for example, the very largest car, they have the control suspension system lah. So you can control the amount of damping to ensure that you receive the best lah. Okay, that one is for the control system. But for the mechanical vibration, the system is input, mechanical system, and output. So input, which is the force applied, and then the mechanical system, which is the properties of the system itself. What is natural frequency? Okay, there's the mode shape and also the damping lah. And then the output how it's vibrate. Okay, so that's how we define the mechanical vibration system. So normally we call as an input, this one is transfer function, and then this one is output. Output is which is the vibration response, how the system respond. So for example, you induce the force. Okay, you induce the force at the force considered as the oscillation force because we know that for the rotating machinery, for example, if you give the rotates the system at a certain frequency, and the frequency have coincide with the mechanical one of its natural frequency, which is this one is mechanical system lah. Okay, or its transfer function, and then the output you will get the higher vibrations. So that's the concept lah. So the higher vibration, which is output here, is can either is come from the mechanical system itself or the input. Okay, so normally for the the faulty machinery, okay, the faulty machinery, which is there is a defect on the machine. Defect on the machine can also induce the high input, the higher input. So the higher input, no matter how about the mechanical system, it will relatively can produce the higher output lah. So for example, if you have the fan system, the fan have the unbalanced mass. So unbalanced mass, which is the fan is not the imbalance. Okay, the imbalanced fan we once it's rotate, we create the higher vibration. Okay, so due to the imbalance of the system. Okay, so which is the, for this case, it reduce the higher vibration force lah. Okay, so higher rotating force is due to the unbalance. So higher rotating force, which is without the higher inputs. So higher input, we automatically we produce the higher output. Okay, but if the higher input and what the frequency of the input frequency of the rotating force is coincide with the one of resonant frequency, the problems can be the worst case lah. So there is higher input and plus resonant, and then it can amplify the input force, which is can produce very high output. So that basically the vibration system. So if you want to solve the vibration system, you have to identify the problems. So it's either come from the input or it's the mechanical system. So the output is what you are measure. So you put the sensor, you sense, and then you found what is the vibration level, what is the frequency of the vibration. So you found that if the frequency doesn't coincide with the natural frequency of the system, then most probably the high vibration is due to the defect of the system. Okay, so which is there is any component defect. For example, the unbalance issue, the misalignments. So actually this one have their own standard lah. For example, if there is the unbalanced issue, so we found that the outputs dominate by the speed of rotational lah. So for example, the fan speed, if the 10 hertz and you found that the output have the higher response at 10 hertz, more probably is come from the unbalanced issue lah. Then if there is a 2 times of the rotating speed, and then it might come from the misalignment issue, and that's the way we diagnose the vibration lah. So we detail, we go after this. So for your lab session, we introduce about how to identify the unbalance issue and how to solve lah. So your lab session, we start on week 3 lah. So week 3 we give the briefing, you form the group, and then you can start your project independently lah. Okay, so I think that's all for today's session. We are already at 10 o'clock. Okay, so that's all for today's session. Thank you. So before you leave this room, make sure you write your name and your matrix number lah. That's for my attendance record. Okay, so any questions so far?
No, sir.
No, sir. No, sir.
Okay,